one. And please consider becoming an AFCOM member. You don't have to be to attend the meetings, but it does help support the meetings. If you become a member for events like this, for National Data Center World, when we can actually meet each other face to face again. There's a great trove of research that I've just started to dig into that's free, available to us. And there are about 1,500 of your peers who are members. It's a great networking opportunity and a way to give back to the industry. And Dallas Fort Worth, AFCOM.com is a way to find out more information if you would like to. Can you go on to the next slide, please? We've got five objectives or five takeaways, questions that I think you may have had coming into this. One is demand. We've been talking about high density cooling forever. Is it really here yet or not? And when will it be if it's not? Cost. Is it cost effective, or is it going to cost you an arm and a leg? How does it work out on cost compared to just air cooling? And efficiency. How will it impact your PUE? Maturity. We've got a bunch of different options, approaches to the same question here, same goal. And are they prototypes now? Are they in production? Are they being used? You'll learn that. And then for an evaluation of all the different options, there's such different directions you can take. How do you figure out which one to take? And is there any way to compare them? So those are five things on a high level that I think you'll come away with this with. And our agenda looks a little busy because it is, but we've got first, well, you could read the different subjects, and these have been rotating while you're waiting. And at 5 o'clock-ish, we'll be back for the panel discussion. And we'll start off with an overview from Nigel Gore, all the way from the UK with Vertiv. And he's got an amazing, background of experience in high density and liquid cooling and this whole subject. And he's going to look at, is there demand for high density cooling, and what do the solutions look like? Take it away, Nigel.
Thanks very much, Al. So my name is Nigel Gore, and I'm from Vertiv. For about 5 years, I've been focusing on liquid cooling technology, focusing on cold plate and immersion. Most recently, I've been involved in autonomous aerial vehicles and robotics. And other background experience has been 15 years in IT OEM hardware, where I was responsible for product lines across emerging technologies in telecommunications, mobile computing, and servers. In terms of industry contributions, I've been working and collaborating with the EEHPC working group on guidance and specifications, and with the Open Compute project, working in the Advanced Cooling Solutions group, also supporting with guidance and specifications and contributions to the development of the liquid cooling industry. So in terms of applications for and drivers for high density, I think what we've seen is an incredible growth around digital technology and the digital economy, and that spurned new technologies around artificial intelligence, machine learning, and high performance computing. But what we're seeing is that it's not just been dedicated towards academia and science labs. It's going beyond that. And some examples we've seen are within cloud-based HPC, where you can do simulations and modeling online. And then in cloud gaming, we can get real action-packed entertainment, rich media, and low latency online as well from your home. Other benefits have been within the fiscal and finance industries, where you have trade automation as well as automated stock analysis, and significant benefits from fraud detection before it's happened. So a lot of analytics going into it, a lot of HPC being used in those industries. Another example to illustrate the demands on the computing performance is what we used within developing autonomous aerial vehicles. We use digital twins, and we modeled in essentially the entire environment that the vehicle was going to be flying through, and it needed to be able to model based on its characteristics of the vehicle, from its fuselage, its wingspan, material type. And we also needed to consider, how it would do its situational awareness. So we had, computer vision to pick up imagery and do the detect and avoid scenarios that it would need to do. And then we do a flight profile from pre-takeoff to ascent to cruise, and then down to as it would reduce altitude, descent, and then land. And as we were looking at this technology, we were able to formulate and simulate various scenarios, change the characteristics of the material types, change obstacles, etc. And that requires a huge amount of data. It's all connected neural networks, and that's placing a significant burden on the compute technology that we had. If we go to the next slide, we'll talk about, what is that IT equipment technology? What is the density and thermal design power? So when it comes to density, what we're seeing is that low latency to try and transmit and communicate those high bandwidth data sets to benefit from that low latency for the communication is really driving innovations around the computer components, the processors, the accelerators we're seeing today, as well as the memory and communications efforts as well. And these low latency requirements is really networking on the component codependency. And this dependency is basically bringing the components closer together, and new packaging paradigms are coming into effect. All this combined is driving and raising up the power and performance benefits that we've seen. If we have a look on the right hand side, there's the top right hand side. There's two examples of server socket configurations. The one on the left has as the example of a two CPU socket, and on the right hand side is a 6 socket where there's 2 CPUs and 4 accelerators. So when we're looking at thermal design power and what is these new component technologies do to the overall power displacement on the servers and the thermal design power that we need to try and cool, we then look at all the components and we start calculating them in the table, and you can see each of the individual main components there, and they've been extend between 2 to 6 socket systems. We move between 800 and 800 watts all the way up to 2 kilowatts in a server chassis. Now that's certainly some mainstream top performance SKUs that we're seeing now. It's not the highest performance. We have seen 400 watt CPUs on the market, and there's new accelerators coming in. We've seen on most recently at the Open Compute Tech Week, a new accelerator module being developed for artificial intelligence that's supporting up to 700 watts. Now, when we look at that and we extrapolate that into the heat density, that has a possibility to offer in a 1U format 6 kilowatts of compute capacity. So that is a significant heat loads that we need to cool. If we look at new approaches to cooling on the next slide, we start to look at two differentiators. On the two liquid cooling technologies, we're seeing the cold plate technologies and immersion technologies are being looked at for high density cooling. Within the cold plate technology, we have single phase and 2-phase. The variance here is that within single phase, the liquid doesn't change state. It remains a liquid through its temperature boundaries. And within 2-phase, it changes phase. So it moves from a liquid or the fluid type through to a gas, and it condenses. And through that condensation, the cooling effect happens. So those are two broad categories around the two different cold plate technologies. And then you need to bring it all together. You have a central cooling distribution unit within the data center. Now, all of these work together. So the cold plates, the headers inside the rack, you can have rack CDUs to distribute the fluid, and then the row-based or central CDUs or liquid-to-liquid CDUs will then all form part of the solution set. And we'll talk a little bit more detail on those technologies. On the immersion technologies, we have Taylor Monig from TMG Core, who will go through the direct-to-chip immersion side, where he'll go through and share some experience around their solution around 2-phase. But within immersion, you also have single phase single phase fluids. They, similar to what I described on the cold plate side, don't change phase. They maintain a liquid through various temperature boundaries, and then two-phase pertains to gas. And those are packaged in either a tank version or within an IT chassis version. Next slide, thank you. So in terms of cold plate technology, if we look at cold plate, it needs to mate to a flat surface. So it really suited towards CPU accelerators where there's a flat surface to mate the cold plate to. And then the other consideration around cold plate is that there are two opposing forces. One is managing pressure drop, and the other one is to manage the surface area of the cold plate. And whilst you want to manage and reduce your pressure drop through the system as you flow liquid through the cold plate, you want to pick up as much heat. So you want to have as much surface area on that cold plate. So they manufacture the cold plates with fine fins with a very narrow fin pitch between the cold plates. These reach up to 100 microns. So very, very narrow fin pitches for the fluid to pass through. So that's working to try and generate and capture as much heat off the components as possible. And then again, we look at the two different types of fluids that can be utilized. Moving on to the other components that we need to consider when we're deploying liquid cooling within the data center, as we need to consider the cooling distribution units. This is on the next slide. So just high level here on the CDU. So the cooling distribution unit is fundamental in distributing the fluid through the facility to the racks, and we want to make sure that we can provide enough fluid at the right head of pressure through to the racks to be able to support those high density cooling requirements. And then a couple of aspects around cooling distribution units, especially when it comes to cold plate. Now we have that need to ensure that fluid doesn't have any contaminants or debris. So these are picked up by very fine filters. They're typically 50 micron filters built into to the CDUs. And these ensure that no debris come into contact with those fine fin pitch on the cold plate side, and therefore potentially can corrupt the cold plate. So these smarts around the CDU development now has these 50 micron filters built into the CDU, which you can do and concurrently maintain. So there's no downtime when you're replacing these filters. And that's a key thing to look out for when selecting a CDU. And then other areas is that the CDU is maintaining the temperature set points that you're required to keep the IT equipment within its operating boundaries. And that's essentially then connecting with the primary heat rejection interfaces as well. So some really important other aspects are the rack manifold, and these are certainly developing and moving forward. We're having rack manifolds now which are allowing for blind mate connectors, so you don't have to concern yourselves about maintaining couplings and hoses, and these are allowing for very quick release in certain and release of the circuit brackets and reducing the form factor. Thanks. Next slide. So I think in summary, we look at what's been driving the compute density, and we can see that it's been innovation in the digital technology from those applications that we described. And then IT equipment is raising its heat load. There's a lot of compaction happening within the IT server hardware and telecommunications and communications hardware. And we're seeing overall we need to get closer to the heat load, and cooling strategies that we described around liquid cooling are certainly supporting that approach. Thank you very much. Over to Taylor Monk.
All right, well, thank you, Nigel. It was very well done. Nigel was gracious enough to tell us all why immersion cooling is coming into play. So I'm going to focus just purely on two-phase immersion. I'll wait till the slides come up.
And Taylor's company is TMG Core. We've watched their technology develop from the beginning, and they've got some very bright, creative people who've really moved at lightning speed to put together what they put together. And it's evolved from me. You go back 2 weeks later, it's evolved again. I mean, it's evolved tremendously. put
Yeah,
together.
we're a 3-year-old startup now. We focus solely on two-phase immersion. I've had the great benefit of meeting Al, and thank you guys for having me to talk with you guys about two-phase. Yeah, so today we're going to talk about two-phase liquid immersion cooling. There's a graphic here up on the screen that'll walk you guys through this. But basically, what we do is open bath or direct to chip, as Nigel said. So it's an open bath of fluid. The servers are going to sit in a vertical orientation inside of the bath. And the basic process, and it's much more complicated, I'm going to distill it down, is essentially the servers are going to generate heat. That heat is going to be transferred into the fluid. And as that fluid reaches its boiling point, the fluid is going to turn from a fluid to a vapor. Now we have a wide range of boiling points of fluid, depending on if you're running ASICs or standard computer, whatever it is. So that boiling point can vary a little bit. But as it turns into a vapor, that vapor is naturally going to rise past the fluid line, and it's going to make its way up to the condensing coil that is inside the tank. So the tank is sealed. That condensing coil is going to have water with a lower entry water temperature than the boiling point of the fluid, causing a low pressure zone up in the top of the tank. So our most common fluid that is used by our customers is FC72, and it requires an entry water temperature of 86 degrees Fahrenheit. So we're talking about warm water cooling. We don't need chillers or anything like that. And as that low pressure zone is created, the vapor is just naturally attracted to that coil. And as the vapor touches the coil, it transfers the heat and turns back into a fluid, dropping back down into the bottom of the tank. Fundamentally, this is the most important part about two-phase liquid immersion cooling, being that the cooling process within the tank is happening naturally, right? The heat is rising due to convection. The low pressure zone is creating the force to touch the vapor to the coil. And essentially all of that cooling is quote unquote free. As that heat is transferred into the coil, we have the water running through, and that water will take that heat out of the coil and it will make its way out to its final heat rejection. Most people are using dry coolers or water towers, just depending on the situation. So that's a very basic understanding of how the systems work. On the left side, you'll see some of the benefits of open bath immersion. Obviously, is just the extreme density capability with it being an open bath, and one of the most interesting characteristics of this fluid being it just naturally fills in any void created by the bubbling. It opens up a lot of opportunity for server design and densities all the way down to the chip level, making modifications that can truly just make a more efficient data center. I think the main reason why people are attracted to two-phase immersion cooling is obviously the PUE numbers are extremely low, given that cooling process inside is natural and you're just having to flow water. Some of the things that make us well known or we're famous for is obviously our robotics. So given the immersion nature and the servers fitting vertically, we've came up with a cable-less backplane design that allows for robotics and switching out of the servers when components fail. We're able just to have a robot go in and pull them out. It's one of my favorite pieces of the equation, because when you're working with immersion, the ergonomics behind dropping a server in a tank is just, it's not something that is natural. It's hard to do, and the servers weigh a lot given the densities that we're trying to create. And some of the challenges, the biggest one being vapor containment. There's two ways to do it. You can have an atmospheric or a pressurized system. From my understanding, TMG Core is the only company that's ever designed, built, and operated both atmospheric and pressurized two-phase immersion tanks at scale. So we have a great understanding of the pluses and minuses of going either way. And at the end of the day, we might be a technology company, but something that we focus on a lot, and a big part of our patents and value is in vapor containment and in managing that vapor. So that's something that we focus on a lot here. If you could go over to the next slide for me. All right, so I wanted to give you guys a little background, not only about myself, but on TMG Core and why you should listen to us. So in the middle of the screen there, you're gonna see our first generation two-phase technology. So this was a pressurized system. They were 1 megawatt skids, 2 500 kW tanks, one on each side. They were bolted together in the middle. We did a 415 straight to 12 volt DC conversion into the tank, which saved a lot of money on the electricity conversion and also provided that density. So this is 1 megawatt and 520 square feet. This fluid that was used in the deployment, it was ran for 2 years, was Novec 7100. These systems were not hot swappable. You had to shut them down to repair them, or if there was any components inside that broke. Like I said, we operated this system for about 2 years. We brought in a lot of people to see it and give us notes on it. And what we did is we took all of those notes and created what you'd see below. So this is our second generation of two-phase immersion technology. It's an atmospheric unit, meaning that it breathes. It has a bellows bag that literally expands and contracts as vapor is either formed or a negative pressure is created. And it also has our patented vapor recovery system. So we're the only people in the two-phase industry that don't use bellows for the full vapor containment. We have a patented vapor recovery system that we use that fits inside the unit. There's no bag that needs to be put into the ceiling or some of the other proposals that our competitors have come up with. It's all inclusive inside that unit. It's fluid agnostic, so it's designed to work with fluids as cold as 3284 from 3M all the way up to, let's call it an HT70 from Solvay. So a very wide range of fluid can be used, and the coil is sized to appropriately cool each one of those components. It features two 60 kW racks with 10 auto immersion units, and I'll touch on the immersion units later. And it's fully redundant. It has robotic hot swapping, so if, it can be sitting out on the edge. You will not need an operator to go out if you have a server down. We have a rack that's sitting there. The robot can go in, grab a server from the rack, transport it into the tank for you, cableless, backplane, so you don't have to have any people there. It'll turn on automatically and go back to whatever it was doing before. So those are the two units that we've developed. We have a number of other products, but I just wanted to highlight those two as the ones that have been out in the field and have been working and we have our experience with. On the right side, I thought I'd include something just generally interesting and also a nice visual for people to understand how two-phase immersion works. You can see the boiling process there on the chip. What you're looking at is called a boilerplate. So it's the immersion replacement of a heat sink. In the early 70s and 80s. So two-phase immersion has been around for about 40, 50 years now. IBM was messing around with it in the late 70s and early 80s, and a number of people ran into the problem with these boilerplates. Luckily, over the last 20 or 30 years of material sciences and things like that, we've been able to develop these boilerplates and they work absolutely fantastic. The general concept behind them is just expanding the surface area that is on the chip. So the fluid will take in on just a flat surface about 14 watts a square centimeter. Using this technology, we can drive over 50 watts a square centimeter, and it's something that we're actively doing research on with goals to get up towards the 70 to 100 watts a square centimeter. And that's a little bit about us and what we've done over the last 3 years. If you go into the next one, this is when things get more interesting and get a lot more creative, right? So the slide got a little bit messed up there. I apologize, I'm not sure what happened, but two-phase immersion, robotics, and automation changes the way that we can build our data center. So just really allows you to completely rethink how you're gonna lay it out, what the costs are gonna be and what the efficiencies are gonna be, right? So we can start with the glaring obvious point, which is just a massive reduction in square footage. And moving into this new age where people are trying to lower carbon emissions, starting with a building that's 1/10 the size, that used 1/10 of the concrete, that used 1/10 of the water, had less trucks driving to and from the site. All these things add up to just having a lot lower carbon emissions from your data center. When you're thinking about how you're going to lay it out, you're going to have no raised floors. All immersion tanks, both single and two-phase, can just sit on hard concrete. There's no reason to have any sort of raised floors or anything like that, so you can eliminate that cost. Minimize your air handling. Obviously, a majority of the compute in our case is happening within the tank, and there's really no reason to keep a massive air handlers in the data center. You only need to keep the tanks at the same point of the boiling point of the fluid, so you can keep them warm. You'll honestly be putting in air just to have creature comfort for the people that are working for you. And then another big one, when you're thinking about what is a data center, or how are you going to make a data center, when you have this reduction of size and supporting equipment, it really allows for you to get creative with your options, especially on the edge, right? So talking to some of the points that Nigel brought up with cloud gaming and things like that, they need low latency. Immersion allows you to put a whole megawatt in a high, on a skyrise in the middle of New York and provide low latency connections to, all of your customers that are within that city, which previously with air cooling, probably wouldn't be something that we could do. So there's a lot that goes into how you could design your data center to take advantage of immersion. And if you could go to the next slide, this is what inspires me the most, and it looks like some of this stuff got messed up in translation. So you'd go down, you basically take benefit all the way from the data center level all the way down to the server level, right? And what we basically want to do is take advantage of every opportunity that two-phase immersion provides. So we'll start in the top right. That's a rack. It's a completely different rack. It doesn't look like anything that would be in the data center today. And that's why the board was designed. for two-phase immersion cooling. The rack was designed for two-phase immersion cooling, the tank that it sat in, so it used minimal fluid, was sitting in the vertical orientation with obviously 2,000 watts of board stacked 12 millimeters apart, really slamming everything together. To your right, you'll see the heat sink versus the boiler plate. I thought that'd be a good visual for people just to show what we can do with densities. That's one that I personally took off a Tesla V100. And then in the bottom right, you'll get into our HydroBlade form factor. So like I said, you know, Team G-Core doesn't just build two-phase immersion cooling. We were trying to inspire and create what could be the most efficient data center possible. So we came up with this HydroBlade form factor. It's basically 6,000 watts of power and cooling per blade, completely cableless design that you just stab into the back plane. And we have a couple of different varieties that we'll be releasing this year. Over to the left side, this is one of them. This is the project I'm most excited to be working on right now. It's a server that we're releasing called the C841. If you went back to Nigel's slides, looking at 2,000 watts a box and having a couple nodes, this is a 12 Walker Pass CPU nodes. It's a AP product, meaning 2 dies on you know, in one chip. So it's technically having 24 CPUs in a one auto immersion unit. Almost 700 cores in a single box, no fans, and you know, robotically hot swappable, taking the fans and any sort of spinning hard drives away inside the fluid, basically make it so servers do not fail, which is one of my favorite parts about immersion. Is it's a completely clean, stable environment that the cooling is happening naturally and the fluid is filling in. All of the gaps that are being created allow us to do creative things like this, like putting the 12 nodes in, the boards are double stacked, the power supply is in there, and it's just a different form factor. So yeah, that's my last slide. Just wanted to give you guys a basic on what immersion cooling and then what advantages we could take from immersion cooling to, you know, build a better data center of the future. So thank you for giving me your guys' time today and listening to my talk.
Thank you, Taylor. For our next one, we'll be going on to Nautilus Data Technologies. And this is one that most of you probably heard about and wondered, what in the world is that? One of the things they do is, you know, they've actually floated a data center. So they're using water in multiple ways. And Chad Romine, who's a co-founder and vice president of Nautilus, will be presenting that to us now.
Perfect. Thank you, Al. And thank you, Taylor and Nigel, for your presentations. If you want to go to the next slide, I can. So I just share this slide just as an example, as we're all well aware of that, how data centers have evolved, right? From being in the closet to the basement to the building next door to now they're, you know, large industrial processes, basically. Mm-hmm. What we have done at Nautilus is every other industry in the world that generates heat for the last 100 years, whether it be power plants, whether it be agricultural, manufacturing, petrochemical facilities, ships, right? They've used water to cool. Data centers, on the other hand, they grew out of the commercial real estate sector. And so these commercial real estate developers, what they were comfortable with and knowledgeable with was air conditioning and moving air and hot air and cold air. And things have worked, but now, as we're all aware of, data centers now are no longer a nice to have. They're now an industrial process that is required for society to function and succeed. So if you go to the next slide. So at Nautilus, again, what we've done is we've borrowed, you know, trusted and true-worthy pre-existing industrial cooling processes with some engineering and ingenuity, right? We've been able to apply that and patent it now towards the data center and water cooling data centers. So the hurdle we overcame, right, is as you see on the top here, the current traditional data centers, they consume public drinking water supply, evaporate water, use chemical refrigerants. The average PUE is about 1.4 to 1.6 for a multi-tenant type facility. And with Nautilus, we've been able to eliminate those processes. So we do not tap into any public drinking water supply. We evaporate no water. We use no chemical refrigerants. We actually guarantee our customers a PUE of 1.15, and that PUE is 24 by 7 by 365. It's not an annualized PUE. And there's actually a couple locations that we're working on where we will guarantee a lower PUE as well. But for this discussion, really, it's what this industrial process has allowed us to do now is we're able to scale out HPC environments on a massive scale. You want to go to the next slide? And so Nautilus's approach, think of us really as just the last mile. We're agnostic in the different types of cooling that folks and customers are interested in. So we really just want to be that last mile delivery of Mother Nature's cold water. So whether you're looking at rear door, direct to chip, immersion, we at Nautilus for our initial data centers, we're actually using our U-Systems rear door. We're very happy with. You want to go to the next slide? So this is just a rendering of a land-based, one of our land-based data centers. As you can see, we've been able to eliminate all that exoskeleton mechanical infrastructure there that you see. We don't have any water chillers, treatment facilities, crack units, you name it. We literally just have an open loop. You'll see on the right of the screen there, that's just a depiction of we just need to be near a given water source. And we have an open loop and a closed loop system, and we do the heat exchange between those two systems. So the water in our open loop system, we are water agnostic. Again, we're just borrowing Mother Nature's cold water. So we don't care if the water is fresh, brackish, salt, sewage, doesn't matter to us. As long as roughly it's about 75 degrees Fahrenheit or cooler, we are perfectly fine to stay within ASHRAE standards. As you can also see, similar to what Taylor was mentioning in his presentation, because we are literally just pumps and pipes, and we've been able to eliminate some of the mechanical infrastructure, we are much smaller. Our footprint is much smaller. If you go to the next slide. So this is just a view of inside the data center. On either side of the data center hall there, you'll see our cooling distribution units. That's the open loop and the closed loop coming together. And that's where we do the heat transfer, the heat exchange, excuse me. Then we move the water into the closed loop system of our data centers. Because we're capturing the heat just as its earliest exit point, this has allowed us to really have no space between our racks. So regardless if somebody is running a 10 kW rack next to a 40 kW rack, we are perfectly fine with that. So we're able to improve the rack count within a given floor footprint. You go to the next slide. And so to Al's point, this is what we've gotten some attention on, is because we are just literally a cement pad and walls and pumps and pipes, right? We now have been able to build these data centers on barges and deliver them anywhere in the world. This is actually a picture of our first data center that was tugged from Vallejo, California to Stockton, California, all in one day. And we permanently moored it. That's a 6 megawatt facility. If you go to the next picture, this is the picture of the data center that is moored. And so really, again, I just wanted to reiterate everything that you're used to about data centers in regards to dual path fiber and power, right? Electrical, that is all the same. Again, Nautilus, what we have done is really, we've just brought together the delivery system for the water into the data center. You go to the next slide. This is just a picture. This is an older picture. I apologize. I should have updated this picture, but I just wanted to share with you again, if you go to the picture on the right, you'll see on the bottom left, that's where our backup generators are, the parking lots next to that, and then the building that you see is our NOC as well. And again, there's the data center that's permanently moored. So we are, my president, Rob Flegging, is actually in the process right now as we speak, finishing up the commissioning of this data center. So we go live in about 10 days.
Okay.
That's it.
Okay. Thank you, Chad.
Yep.
Yeah, and that's exciting to, after all this time, be going live.
It's been a great journey.
Yeah.
I'm glad to be there.
Yeah, congratulations. And for our next one, we'll have Paul Sertikowski with U-Systems, a company from the UK, but with a very significant presence in the US. And they have rear door cooling that I kind of feel like somebody challenged them and said, oh, you can't go over X kilowatts. And they said, oh, yeah, we'll show you. So, Paul, what are you guys doing? Thank you.
Well, yeah, thanks, guys. Also, too, I've got my colleague Gary and my manager on the call as well from the UK, so it's late for him. So thanks, Gary. But I'm based in Atlanta, like I said, or Al said. Thank you guys for your time. Is the slides up yet? Oh, there they are. Thank you. So use systems, right? Next slide, who we are and what we do. So we are a true manufacturer of data center cooling in the industry, right? So today I'm focusing on our ColdLogic rear door cooler. So with that, 3 points I wanted to address. One being how the rear door cooler, ColdLogic rear door cooler, can do low to high kW cooling on your site, anywhere from 1 kilowatt up to 200 kilowatts per rack. Doing that via our smart passive rear door cooler and our active rear door cooler. Point number 2 being deployment of ColdLogic rear door coolers. So there's a strategy that we've been using a lot, and it's been proven. And we've got a great CFD study we'll show you here in the slide. Shows how you can deploy the rear door cooler one every 2 or 3 racks, depending upon the load in that environment. And the third point being the efficiencies and sustainability of the rear door coolers, being the ROI and TCO. Next slide, please. Some of the myths about rear door cooling is we're kind of pigeonholed in this 20 to 50 kind of high density area, which is not really true in reality. Next slide. We can go anywhere from 0 or half a kilowatt up to 93 kilowatts. And then with our new product being released, which is our CL200, up to 200 kilowatts. The next slide. So looking at the smart passive, this is a rear door cooler that basically, you look at step 1 to the left, is up to 35 kilowatts of cooling. It's 100% passive, so no fans, no power consumption. So for a great PUE number, deployment of this rear door cooler can be used in different environments, relying upon the server fans to push the heat through the actual rear door cooler itself. What we did, though, we relaunched this product last year. We made it a smart passive door. So if your customer deploys the passive door at first, step 1, and then say a year down the road or 2 years down the road, their end user changes out the kit, the gear, servers, and they're having heat dissipation, airflow issues, we can then populate that passive door with fans, brains, and we can then control the power. We can monitor the water flow, fan speed, temperature, so we can then turn it into a smart dumb door into a smart active passive rear door cooler. Next slide. Looking at the active rear door cooler, so this one, we can go anywhere from half a kilowatt up to 92 kilowatts per rack in a data center environment. Do that with very energy efficiency, reducing the OpEx for cooling and increasing your white space in your data center. How it can be so scalable, real life example is you can deploy a rear door cooler on any rack. Say you're doing 10 kilowatts day 1, and then 12 months down the road, 2 years down the road, your end user wants to go to 20 kilowatts or 30 kilowatts. That same rear door cooler on that same rack, if you change the infrastructure, tweak it a little bit, can go from 10, 20 to 60 kilowatts per rack on the same footprint. Next slide. The ColdLogic rear door cooler, whether it be used in a new build or retrofit, some major benefits and advantages. You look at the water flow. We've done bake-offs with our rear door cooler against other manufacturers of cooling doors. We use 50% less water flow needed, which, what's that mean, right? That results in massive, smaller outside plant facilities, massive savings, smaller pumps, piping, chillers, etc. The cooling also too with our cooler is done with warm water, right? So no more days where you need to have 45, 55, even 60. We're looking at 68 to 75 degree entry water temperatures. So what that being is your site can then actually use the return water in the environment to cool racks or rows. So no new flow needed. You can send the higher water temperature outside, so you have a bigger delta T, of course, which makes your outside plant run more efficient. And the biggest benefit of this is free cooling, right? So a lot of environments don't even need chillers anymore, just free cooling in regards to the rear door cooler using warm water. Next slide. So this is our new product here. It's our ColdLogic CL200. And actually we have one that's going to be on Chad's barge here shortly, being tested by a large HPC customer. But this is our new release. Working, environments who don't want to roll out chip level or immersion. This is a great solution where basically it's an easy deployment, a 52U rack, 48U, 800 wide. It's got massive savings on both the ROI and your total cost of ownership. It's got very easy and better SLAs compared to the marketplace in this high density cooling. And basically look at it, 5 racks being 800 wide, you have a 1 megawatt site. So it's one of our new products. We're very proud of it. And not that everyone needs this 200 kilowatts per rack, but it is available. Next slide. So this is interesting here. What we've done for some of our major customers, some major colos in the area, have looked at deployment strategies of the rear door coolers. So in this environment here, you can see it's 14 racks in this pod. It's what, total of 260 kilowatts. But you look at 6 racks at 30 kilowatts and then 8 racks at 10 kilowatts. So in this environment, with the infrastructure down below, all the stats, we can actually cool the whole load with just 6 rear door coolers. So if you go to the next slide, you'll see the CFD study showing this. And we've done this with, you can go next slide, Jared. You'll see we've done this with the CFD study showing where we're in ASHRAE limits, right? So we've done this with rear door coolers on 1 every 2 or 3. We've done it every 2. So we'll see where there are studies where we are out of ASHRAE, but in most environments, we can back into the solution with less than 1 rear door cooler on a 1-to-1 ratio. What does this do? This basically gives the end user a better capital outlay of a budget and also a better ROI and total cost of ownership with their deployment of rear door coolers. I think, and so last slide. So it really, in summary, with the rear door cooler market, right? I mean, I think the big benefits, it's warm water. There's no more cold water. You can use return water in a data center, anywhere from 1 kilowatt to 200 kilowatts. It's a closed loop system, very low flow water, no CDU needed, attaches to any rack, can be passive or active. And then when you look at the actual operating expense, energy efficiency up to 96% reduction compared to traditional cooling. Space efficiency is 90% easily because our rear door cooler sticks off the back of the rack 13 inches, that's it. So we increase your footprint and increase capacity of cooling. I mean, in the same rack, you can go from 10 to 100 kilowatts without having to ever, lay capital outside infrastructure just by moving your water temperature around. So that's really it for the U Systems rear door cooler. I know Gary will be in the panel as well later, hopefully answer any questions as well.
Thank you, Paul.
Hey, Al, we got our first question. Do you want to open up for questions or keep rolling?
Let's hold for the panel, as
Okay.
we said, but those can be the first questions when the panel starts.
Okay.
Thanks. Yeah, and for our next, we've got Sherman coming up with Future Facilities, and he'll be talking about the digital twin. And it's a product that really, a solution that really applies to all these products and even products beyond this in terms of with all these different ways you can cool. How do you figure out what makes sense for you? And Sherman's got some interesting thoughts about that. And you're on mute, I believe.
How's that? Is that better?
Yes.
Okay, great. Thanks. All right. Thank you, Al. Thanks, everyone, for joining. My name is Sherman Ikimoto. I'm a managing director at Future Facilities. I'm in San Jose, California. If we go to the next slide, I can introduce the company. For those of you who don't know, we're a software company and also a services company, engineering services. We've been around since 2004. Our main core competency is simulation software, and we'll talk about that in more detail, what that means. We're the only simulation company dedicated to the data center industry. Our vision is a world where all data centers are able to realize their business potential. We'll talk more about that later. And our mission is to deliver digital twins to every data center, make this a standard in the industry. And also through this digital twin concept, organize and connect the data center ecosystem through simulation. And our product line is called Six Sigma DCX. Next slide. So let me just provide a quick intro. So digital twin is, what we see here on the screen is a timeline, a data center timeline from start through design build all the way through end of life. And digital twin is meant to mimic the life cycle of a data center from start to end. And so you see the physical world below the timeline and this virtual world of digital twin above it. So in the design phase, digital twin concept is used to design facilities. It's also used to design the infrastructure products and the IT systems that go into data centers. And those components become digital twins themselves. and then they can be transferred to owner operators for integration into to form data centers that the owner operators are operating over 10, 15, 20 years. Next slide. And the problem that digital twin is meant to solve is to change the current planning process from one that is broken up into silos. So we see 4 common silos: networking, space, power, and cooling. Those planning processes are usually done independent of each other now. And they're also, the plans are driven by the highest priority silo. So if networking goes first, then the design gets, or the plan gets set by the networking requirements, and then space goes next, which sets their requirements, and then power, and then usually cooling is actually at the very end, which has the most difficult time meeting its requirements because everything was set in advance by the other silos, and there's no more wiggle room for cooling to achieve their requirements. So that's the current practices today. If we go to the next slide. So digital twin consolidates all of these plans into this virtual replica model and enables all of those plans to be simulated. Enables the simulation of the data center in operations with all of the plans accounted for. And so you could actually see the data center perform in this planning process before making any decisions on how the plan should be implemented. So it's a completely new way of doing data center management based on simulation. Next slide. Oh yeah, and digital twin, just to mention, is able to connect to live sources of information, live monitoring from the data center. So the digital twin at all times is literally a replica of the data center's configuration today, and then of course also into the future. And it can also integrate with other tools that might be a part of data center planning, like DSIM tools. Next slide. So we have a short video that gives a good example of digital twin. Can you turn the volume up on the video?
It's as high as I can get it. Sorry.
Okay. All right, well, I'll try to talk through it. So this is a digital twin, a real digital twin of a data center. We're walking through it so that you can see how it actually mimics, and it looks like the real thing, but it also behaves like it as well. On first glance, digital twins can look like a DSIM tool. Some DSIM tools have 3D modeling capabilities, but where digital twin stands apart from DSIM tools is its ability, as I mentioned, to mimic the physical behavior of the data center. And this includes how well the cooling system is working, including airflow delivery, even liquid cooling, and also the power distribution of the room. So it's a common environment for all planning personnel, all the silos, to contribute their plans and then see how it all works together before making a final decision. And the challenge today is to meet service delivery, environmental compliance, and utilization goals in the data center all at the same time. Those are conflicting goals. If you go for one, you usually miss the other two, and vice versa. And the reason is because wow, this is moving fast. The reason is because in data center operations, everything is changing all the time. So any design rule you set up is going to be out of date as soon as new IT configuration or IT technologies come into the data center, like high density.
You,
And we're
you
seeing
can
the
share
effect
and
of
hit
that.
pause for a moment if you want to catch up.
Yeah, I think it's paused.
Yeah. Any idea on why it's running so fast? Or are we trying to meet a deadline? Go ahead. I'll try to keep up.
I just hit play. I don't know.
Yeah. Okay. But we've seen the effect of new technologies, new IT technologies in the data center. There was a poll done by the 451 Global Data Center Alliance that showed that the typical utilization rate in data centers, capacity utilization reaches only 56%, which is alarming. So data center operators are building almost 2 data centers for every one they actually need. Operators are still struggling with reliability issues due to thermal and power. And this problem is only going to get worse because rack densities are going to go up. The pace of business is going to increase, and making this ability to deliver services a challenge. So here we're going to go into an example. One change request on a data center timeline, which may have thousands. In this particular example, we're going to try to deploy 3 high density units. So these units require more power, more air, more space than what the data center was designed to achieve. So we're going to see if we can do this. So the question is, can it be done? And what is the best way to implement this approach or these units? Can you stop the video here just for a sec? So this, sorry, I didn't mean to make it go, just pause it. So under today's management practices, they're based on rules of thumb for how to space IT equipment, how to allocate cooling, how to allocate power. If you can jump ahead just a little. Under those rules, this configuration that we're going to see here, if you go ahead, maybe a couple more seconds. Sorry about this. Yeah, this can start right there. This configuration here in the highlighted is a likely way of deploying these high density units. There's extra tiles put in, hoping for cooling compliance. There's actually a new power distribution unit added as well. So this is what an owner operator may do to deploy these units. If we go forward again. There's also other ways to deploy these units. If the owner operator was nervous about compliance, they may try to throw more resources at this deployment and spread things apart, bring more cooling in. So here's a conservative option. If you go one more, just up ahead a little bit. And there is an aggressive deployment. This one, an operator may try if they're really trying to conserve air and space and power. So you can see the difference. The likely, it's kind of in the middle, conservative, spreading everything out. Aggressive is trying to pack it in and conserve resources and capacity for future use as much as possible. So which one do we pick? Under current practices, you may just try to run the video now. Under current practices, we have no real good way of picking from these 3 or any other configuration that we'd want to try. We don't know what will happen. And that's the point. So with this uncertainty, we see service delivery delays, environmental risk, inefficient use of data center resources. So this is where the digital twin comes in. So as I mentioned before, digital twin is this virtual replica of the physical data center. It looks and behaves just like the real data center. It's made up of 2 parts, the 3D model that you see, but underneath is a simulation engine that is capturing the behavior of the data center. So that's what a digital twin is. It's these 2 components together. And now we can go back to that example and take a look at how a digital twin will help us. Well, now we're simulating these implementations, and right away under the likely configuration, digital twin is predicting an environmental compliance problem. And we can zoom in in digital twin and actually see what the problem is, why those alarms are going off. It's a over temperature issue. We can use the simulation capabilities to develop a solution for this configuration. So we find one here that works, adding a cooling unit, and we can quantify the performance and the cost. So there's the performance. It makes it hits compliance, but it has extra costs associated with the cooling unit. The conservative option works. There's no compliance issues, but it's a bit more expensive because we're using more space, power, and airflow in cooling. In the aggressive option, we're conserving space, power, cooling. Now, we find that it does actually work from a compliance standpoint as well. So this was unexpected because nobody on the surface believes you can shove 20 kilowatt racks that close together without overheating issues. But that one works, and it saves on all those resources. So to sum up, we found a way to make all three work from a compliance standpoint, although the most likely configuration required an upgrade. But from a cost standpoint, that's where the differences come in. And it's clear that the aggressive option is by far the cheapest and the best performing. It's easiest to install. Service delivery time is the shortest. It's the best overall. And this sort of visibility of performance, you can only get using a simulation capability like digital twin. And this was just one example on a timeline for a data center that may involve thousands of change requests. Imagine the savings over the life cycle of the data center. So what we're seeing is that with this simulation-based planning, you can increase capacity utilization, sometimes up to 34%, eliminate environmental compliance risk, and also increase service delivery time.
Great. Thank you, Sherman.
Thank you.
It's a great analysis. And now to wrap it all up from the presentation standpoint and be our launch into the Q&A and the panel, we've got Travis Wright from QTS. He's the VP of Energy and Sustainability. And he's got a very good way to look at all of this and summarize it, and then comes up with an interesting dilemma. Travis.
Thanks, Al. Appreciate the time. And for those of you who don't know QTS, we are a co-location data center provider. We have 26 data centers throughout North America and Europe, and it is fascinating to see the technology advance the way it is. If we go to the next slide, I'll show you. This is actually, I'll be honest, this is a chart that I plagiarized from an EPA webinar that I did last couple of weeks ago. I think it's fascinating to see that when we look at a time horizon from 2010 to 2019, you can see data center workloads have increased almost 8-fold and internet traffic almost 12-fold. But the energy use by data centers has remained relatively flat. And you think about that, and it seems mind-boggling that you would be able to do that, but certainly there is efficiency gains by the processors themselves. The semiconductor process has gotten much more refined and much better, and so we're pushing more work through smaller lines, and we're able to get more out of the energy that's being used there. But I also think that a lot of the cooling technology, and if you jump to that next slide, a lot of that cooling technology is pushing us to use less energy in data centers. So next slide. When we think about globally what we put out in front of customers and what we use and what our impact is, it is pretty remarkable to know that 3% of the power consumption, and this, by the way, you can go to different sources and find different percentages here, but this is one that was put together by Supermicro a couple of years ago, that 3% of global power consumption is by data centers as much as the entire UK, and 2% of greenhouse gas emissions, which is equivalent to a pre-COVID airline industry. And you imagine how much flack they take for carbon emissions. Data centers are really right there alongside with them. 10 to 40% of data center load is typically from cooling. Next slide. So I'm going to wrap things up. I'm going to talk a little bit about some of the technologies that we've seen here. Not all of them, but some of them. And so when we think about the way we put a standard data center in place, it's this raised floor solution. Sometimes it's on slab, but mostly a raised floor solution. We're planning for, somewhere maybe up to 20 kW per rack, typically less than that. But it's very simply that air is pushed down underneath the floor, gets pulled in through the front of the cabinet, warms up. The exit air, if you're not using any containment at all, comes out the back of the cabinet, kind of mixes around with the air that's within the environment, and then gets pulled back in through the air handling units that are typically around the perimeter of the data halls. Not very efficient. You can get a little bit better if you're containing either the hot side or the cold side. The little diagram that you see there is a hot aisle containment system where you're actually able to increase your delta T's across the coil and your air handlers and get a little bit better. And so when we design our data centers and put our customers into spaces, we'll generally limit them to about 13 kW per rack without containment. And then with containment, we can get up to about 20 kW per rack, but we typically don't push it much beyond that. The next slide. So then you've got the rear door cooling solutions. Simply we're moving that coil closer to the source of heat. And so the ambient air enters the front of the cabinet, the servers heat the air up, and as the air exits the cabinet, it is cooled. And so by the time it gets out to the ambient air, it's really pretty non-impactful to the surrounding space. And so this is something where we do see, typically we're one of those data center providers who think this is probably in that 20 to 40 kW range. And I've learned a little bit more about the capacities there that we can actually go lower and higher with rear door systems. Next slide. And then if somebody's really looking for some high density stuff, there is immersion cooling. So very simply, servers are immersed in some sort of a fluid. Mineral oil is common. Servers heat up the oil, oil's pumped through a heat exchanger, and then the mineral oil comes back, returns back to the bath somehow. And there's certainly different technologies and different ways to do that, but it's simply a way to do that. So getting up to 200 kW per rack is just crazy amounts of power per rack. And truthfully not something that we have ever seen or done. Next slide. So they make a lot of sense. You can reduce your footprint. You can reduce a lot of your build. You can save energy. There's all kinds of good to this. And then when we think about it from a sustainability standpoint, our PUE, power utilization effectiveness, reduces significantly as we go to some of these newer technologies. A standard air-cooled system, we're usually looking at about 1.4 for our PUE. Rear door, you can get down to 1.2. Immersion or direct to chip, maybe in the 1.1 range. And so when I think about, I put this into perspective and say, let's say I've got a 30 megawatt data center in Dallas, just from a carbon standpoint. And I think about the energy used, I can save 79,000 megawatt hours per year by going from air cooled to immersion. I can save 36,000 metric tons of CO2 if I go from air cooled to immersion. Huge, huge difference. That little picture that you see up in the upper right corner is a visualization. Each one of those blue balls that you see in the pile there is a 10-meter diameter sphere of CO2, which represents 1 ton of CO2. So it's just an insane amount of carbon dioxide and energy that you can save by doing this. And so the logical question is, why aren't we? Why is the colo industry not typically moving much more toward putting high density applications into place? Next slide. The answer to that, there's a couple of dilemmas here. we as a colo provider need to be able to support all kinds of customers. We have to be very flexible in what we're doing. Some of them are really advanced, many are not advanced at all. A lot of them are relocating older equipment from on-premise data centers. We still see mainframes coming into our data centers. There's high density options, but they do require a very different infrastructure. And so if you think about, look at those pictures over on the right-hand side, the top is sort of typical, what we would normally build, the bottom being the direct immersion cooling. That is a very different building. You can't just build one building and have both of those solutions in it. And the truth is that of the 1,200 plus customers that we have in our buildings, I can count on one hand the number that need workloads above 20 kW per rack consistently. There are many that will have one 20 kW rack next to three 3 kW racks and things like that. But to have a consistent need for high density is fairly rare. I think we would build a lot more high density co-location facilities if we had customers who needed it. And I think customers would need it if there were a lot more co-location providers who were providing it. And so there is a bit of a vicious circle there that kind of binds things up. The other perverse incentive here is that the business model in co-location is set up to reward low density. And I say that because when we build a data center, let's say we're going to spend somewhere between $6 and $8 million per megawatt to build a data center. 2/3 of that cost is going to be in the electrical infrastructure. That is our expensive part. So our lease rates are primarily built on the kW of capacity, not the footprint. The shell of the building is cheap compared to the electrical infrastructure that we put into place. It's very heavily weighted toward the kW of capacity. And so by doing that, for a customer to go from 2 kW per rack to 7 kW per rack, really very little difference in their lease rate. There'll be a little bit, there's a little bit of a penalty for using some more floor space, but not a lot. But if they go from 7 to 20, and now we tell them that we need to install rear door coolers or some other style of cooling system, the rest of the building is already built. And so now we have to add something to their environment. It adds a lot of cost to that customer's upfront build. And so it generally pushes that customer to more of a low density environment. And it is truthfully a perverse incentive to keep to keep buying low density. And it does feel like there's probably a better business model out there that would be able to promote this kind of thing. A little bit of a chicken and the egg though. So anyway, that's the perspective I have from a colo side, and happy to answer any questions if anybody has them.
Thank you, Travis. And that sums up the planned presentations, and now we're ready for questions. Jared, I guess if we can unmute all the presenters and then include and then also include Gary Tinkler on the U-System side. And then, we do have several questions in. Please put questions in chat, or if there is another way to get them in, good with that too. One thing I'd like to kick things off with is, in terms of, is this, do we care? Is this relevant? Are people using it now? You hear Travis say he's got 2 clients who go over 20 kW cabinet, if I heard that right, who have the need, and yet NVIDIA is designing chips that are going to require a whole lot more than that. We've heard that in our last presentation on AI, and we've got inquiries from hyperscalers to some of the people on this panel for north of 100 kW cabinet, and they're telling them they need that, we design it. And NVIDIA, I think, has pretty good track record. They're not wasting their time, I believe. And I don't believe the hyperscalers are just messing with the providers. I think they've got a real need there. So how does that square with what we're seeing in the colos?
Yeah, Al, I can take a little bit of that. I'll say that when you get into the things like cryptocurrency mining, a lot of times colo providers will try to shy away from those guys. It's a market where it's easy to lose on as a provider of space, and so we do take on some, but it's fairly rare. And
Okay,
when we do,
can you hold just a second? Can we ask, I guess, people who aren't speaking to mute? We're getting an echo, and hopefully that'll kill that.
looks like we got you muted, Al.
Yeah, Al, go ahead and unmute. I muted everybody again.
All right, well, I guess I'll continue on there. Yeah, typically when we talk about NVIDIA, you're right. The GPUs out there are just blowing heat like crazy. They absolutely need high density cooling solutions. They need pretty warm air. They can do kind of dirty air. You can do a lot of outside air cooling for things like that. And we don't see a whole lot of it in the colo industry just because we kind of shy away from those guys from a financial perspective. The hyperscale clients, so more often than not, they're building their own data centers. Not always, but oftentimes they're building their own. And so when there is a large enterprise client that's building their own data center, they can absolutely do that. And I think they do. And I think that's driving a lot of the industry. The good news is that it's not uncommon at all for those types of customers to drive where the industry is going. It's not uncommon at all for the colo world to be a step or two behind where, the Google and Facebook and Apple and those guys are going with their data centers. And so when we see them transitioning into more and more high density solutions, it tells me that our roadmap is toward that as well, likely.
Yeah, I'll chime in here too. I think Travis mentioned at the very end of his statement when he was doing his presentation, the whole chicken and the egg thing, right? I like to think of like the past, like I don't know how old some of us are, but you remember when cell phones came out, right? Initially, everybody's like, "Oh, come on, who's gonna use a cell phone?" And then all of a sudden, you can have music and emails on your cell phone. That's the dumbest thing ever, right? And now we can't live without it. I know I've talked to a couple server manufacturers, right? And they now are seeing the issue that they have these server folks designing, but they're not talking to the infrastructure folks, right? And data centers, we're the plumbing, right? You could have the best, fastest, quickest chip in the world, but if you don't have the plumbing to deliver that to the folks, then it's useless, right? So I'm finding out more and more that I really do think it's a chicken and the egg thing. I just think that they haven't, the server folks just haven't, you're not able to scale right now, right? I mean, I talked to somebody that they were looking at 100 kilowatt racks, right? But their issue is I can only fit 7 in a data center. I can't, that doesn't help me. I need I need 100, I need 200 in a data center. And so I think we will see it over time regardless. I mean, it's coming however much we want to fight it, but I do think it's a chicken and the egg thing, and the infrastructure folks are catching up to Travis's point.
So,
Yeah,
Greg Stover here. Can you hear me?
Yep.
Yes.
Awesome. So, gosh, 6 months ago, 12 months ago, if we saw a 30 plus kilowatt requirement, it was maybe once a quarter. You go back three to 6 months ago, it was like we started seeing it once a month. I will tell you, Nigel's team is looking at a RFP every single week that's 30 to 80 kilowatts a rack. So there's a lot of momentum building out there in the marketplace. And at the end of the day, we used to build the infrastructure and then we would tell people what they could do. But the world is transitioning rather quickly to the business. The application drives the requirement. The business value of that application drives the necessity of the business to respond. And AI and IoT and 5G and all those things are very high data intensity. They're very latency insensitive. And so we're starting to see a change. And AI adoption is like this much right now. We're seeing the tip of the iceberg. And the easy place to get that addressed is you put it in the cloud. And so a lot of NVIDIA servers and other people, AMD and others that are building these really fast, high requirements, it's starting in the cloud, but everybody here knows cloud is not the cheapest way. It is the best way. It's the most resilient way to get started. And I think most people have a cloud first mentality, but as things mainstream and their use of that application and the business value of that application grows, people are starting to come back out of the cloud and go to QTS and to go to some of these other vendors And, we're seeing, like Travis said, 1 or 2 customers that are testing it. But I think this time next year, a third of all of, we're talking and aligning to what Chad said. We're starting to talk to all the OEMs every day now. And if you looked at our next generation, it's going to be rear door. It's going to be liquid to chip. It's going to be some sort of immersion technology. Taylor and TMG Core, they're very well positioned. I mean, at the end of the day, it's coming. It's real. It's no longer just going to be a niche product. So that's Vertiv's position. I mean, we're investing in all the technologies. We're going to have rear door. We're going to have liquid to the chip. We're going to have immersion technologies, because the reality is we see AI and IoT and 5G driving all of those things to our doorstep very quickly.
Thank you, Greg.
Yeah,
Taylor, do you have, are you delivering? Are you close to delivering, or can you say, I mean, in 21, are people going to be putting your units in production?
Yeah, absolutely. And I guess the point I wanted to make is, we're living on the opposite world of Travis right now, right? Each one of our customers are coming to us with, I've got a really small space. I want to put a lot of compute in there. And, some of our single server designs are more powerful than a whole entire rack in Travis's situation, right? So we're having customers that are trying to get those low latency, to Greg's point. We have a lot of cloud gaming companies coming to us that are looking of, how do we put our stuff as close to our customers as possible? Like in my presentation, I brought up the point of a Skyrise or things like that, right? We have people with, AI, machine learning, rendering is a big one for us, right? And then just to tie into the point, I think it was Chad made, you got AMD, Intel, the OCP group also, and NVIDIA all releasing chips over the next year that are going to be 500, 600, 700 watts. And Intel's doing that on both the CPU and the accelerator side. So it's going to be very soon here in the world where you're not going to have a server that's going to be under 2 kW for some of these applications, and putting them in racks to 6 kW just simply is not going to be the answer. It's not going to drive the efficiencies that people want. And that's when you'll see immersion cooling and some of the cold plate technologies, really drive forward in adoption, because, you have all these people making chips that simply aren't going to work in air in a couple of years. So I think it's a natural progression to liquid. Chad brings up a good point, right? I don't think anyone on this call can bring up a high power, high heat generating object in the world that isn't cooled with liquid other than computers at this point. So I again think it'll be just a natural drive to move over to liquid in the data center.
It's coming quick, Al. I mean, AI and the different uses of it, again, it's really an education process. If you talk to the NVIDIA guys, all their sales reps are data scientists, and they have a gap. They're trying to get a gap between IT and facilities and what you can do with AI, and we're all learning new applications every day. So, a company will adopt an AI technology, put it to use for that limited application, see, holy cow, there's significant value to our business or to our customer experience or our speed and response or whatever the application is trying to solve for. And you can just see it. And the next thing you know is like, well, what else can we do with this technology? It's like all the technology we've dealt with for 30 years. You ask, what's next? And the answer is going to be a lot more AI-driven technologies, very data intensive, and as a result, a lot more high-density compute in all the different forms.
Yeah, when I heard Nigel talking about the use case of drones and simulating that, I was thinking, man, you could fill a football field with calculations of what it takes to compute all that, and then you've got to keep doing it. I mean, just got to be a huge compute load. So yeah, it does seem like we're kind of exponentially moving demands up, and the chip makers are producing for that, and you guys got to figure out how to cool all that.
Well, I had an MRI last week, and they didn't want to send my images to my doctor because of how much it costs now to move these ginormous files. They handed me a frickin' CD to take to the frickin' doctor. But I will tell you, NVIDIA and others are designing desktop versions of supercomputers so that there can be AI in a radiology department. So that stuff can happen on the spot, right? So, it's baby steps, but it's coming.
Yeah, I mean, when it comes to modeling and things like that, it's everything from healthcare to racing, anything from modeling simulations to aerodynamics, right? To what came up on Greg's MRI is the things that people want to bring in-house. And it's a big thing about immersion cooling, right? You can put a lot in a small package, and you can have a tank sitting there in the office and have all of that compute done there down on site, not have to worry about the space you would need to do air cooling or, really any of the supporting equipment. Just flow water to it and you're ready to go.
I think to Taylor's point, you know, the aerodynamics, we've done a number of Formula One teams, and to Travis's point, you know, with data centers, even today, they're not designed to cope with things like that. I mean, we've been deploying since 2007, and 98% of all of our deployments have been on premise in the customer's own facility, simply because data centers are not designed to cope with anything circa, you know, 10, 15, 20 kilowatts max. So yeah, to Taylor's point, you know, where these AI and analytics, you know, crunching the data, you know, for high speed racing, etc. It's just simply, you know, data centers are not cut out for it. So yeah, it's although Greg mentioned it's been coming for a number of times.
Yeah, I mean, QTS and other quality co-location companies, when the demand is there that the business model works, the capital will move right to what we're doing. And you know, their buildings might look a little bit different, but you know, some will stay where they're at and do what they're doing forever. But you know, rest assured, you know, there's colos out there now trying to solve for this problem at scale.
Yeah, we are ready and willing to do this. It's clear that it makes great sense to be high density. There was a statistic that I think Sherman put up that talked about data centers typically being about 56% utilized. That is right. It truly is, and it's not, you know, it's not because we don't want to use it. It's because our customers are all low density, and so there's just not enough space to put everybody where they.
Yeah, they made you a provision a 30 kilowatt rack, and they've never used more than 7. And for you, that's stranded capacity that you would love to sell.
Well, and even for the customer, they're paying for 30 kW, and they're only using 7. And we did actually make the bold step of telling all of our customers exactly how much power you're using and exactly how much you're contracted for, and it's kind of opened a lot of their eyes to say, oh boy, I can dense this up. Great idea. Let's go do that.
Travis, how many cabinets do you see that are only like half full or 3/4 full as well?
Virtually all. Unless it's a hyperscale client, you know, like a cloud provider or somebody like that, they're very good at utilizing the rack space and densing things up. But if it's especially the smaller clients, they're you know, virtually all of them are half full.
So it sounds like
what I would point out is, and this is something that's unique. In the old days, you know, IT and facilities made all the decisions, but today, our clients, the end users, have options. They can go to the cloud, they can go to a colo, they can do it on-prem. There's choice. And you know, us as operators and deliverers of IT and compute, you know, we need to understand that there are options. We do need to be listening. We do need to be talking to our business line managers. I saw some stat like last year, 37% of infrastructure spend was done by non-infrastructure people. So, you know, your business line manager calls Amazon and says, we want to try this, this, and this. And the guy's like, yeah, I'll have that up by Friday. And they'll spin up all the instances and they'll do it and it will work. You know, but then they get a bill when they try to scale. They go, whoa, time out. I really like what we're doing there, but I think we need to do that here. You know, and so the point really of this group, from what I get, and we've talked to a couple of different people with different technologies, the answers are out there. We really just need to be talking to our business line managers, trying to find out what they're trying to solve for, and the people that can solve it are on this call. You know, whether it's in your colo or in your barge or wherever. You know, the good news is we have answers to solve for this. It's the chicken or the egg argument. Who wants to deploy the capital to solve for it first is kind of the answer. But it's there. We can do it all now. You know, we can put 8 50 kilowatt racks in a container and throw it in John's parking lot, and there's a super compute node with NVIDIA stuff there with rear doors on it. So I guess the point is, don't be afraid.
Well, it's a bit different direction, but I do want to answer the questions that were, you know, one of the questions was asked was, what about fear of water in the data center? Is that still a factor, or are people accepting that now? What are you seeing, you know, for some of the people who are putting liquid in the data center, which is just about everybody here?
I think we have to, you know, consider it's going to be an aspect, and we just need to manage it. We need to make sure we put in the right mitigation strategies. and there's technology out there to be able to support it. The other aspects come about being able to design it right. So when you're coming to put water into the data center, make sure you've got the right weather materials list, be observant to that, and follow good quality water management processes as well. And then implement the right technology. So leak detection, leak mitigation strategies, and use quality couplings, and make sure that you're using quality materials to be able to support that.
I think water's been in the data center for a very long time. It's just not widely understood. It's been put around with crack units, since day dot really. As Nigel mentioned, bunding around the outside. I think the question that came from Trez was, about the water being so close to the hardware. And I think what Nigel's just mentioned, as long as you've got the right protocols and the right application, and having it installed correctly, we've done over 8,000 doors globally, and not had any issues. So, touch wood. As long as it's installed correctly, then there's no real issue. And I mean, if people are concerned about, having water in a rear door so close to the hardware, well, God, we're dunking it in the water at the moment. So I think there's less things to worry about.
Yeah, and also we have a product, a negative pressure CDU. We call it the LPS, which is a half a bar under pressure. And Chad's one of our biggest customers for that. So I mean, it can come as low as 25 kilowatt, 50 kilowatt rack mountable AU up to a megawatt on a skid. So we can actually suck the water through the data center under negative pressure. So if there's a breach, hole, pin size, whatever, it fills full of air and remains operational. It's pretty cool.
Yeah, we actually, this has been my life, by the way, for the last 3 years, giving tours, having to overcome this number one question, right? And so thankfully we have, and it's been funny watching the evolution of people initially having a concern, but now we, see it more and more. And I think we've been saying in this call that liquid cooling is really the future for cooling data centers. We actually, when I give tours, we actually open a live valve. And to Paul's point, right, we have the negative pressure in our systems, and so air gets sucked in, no water comes out. So we call it the leak prevention system.
I wasn't in technology a generation or two ago, but weren't mainframes cooled with water? And
yeah, no, they were, and not only that, I always said
in the world at the time.
Absolutely.
Well, and look at all the industrial processes for the last 100 years, right? When was the last time you heard of a power plant flooding or of a big manufacturing facility, flooding with water? So anyway,
we're pretty good at managing it, and I think we're all at an exciting place. I mean, technology adoption is actually the only silver lining that we've had because of COVID is that technology adoption has been increased on quite a few different fronts. So, most of us, if you're not in the airline business or the hotel business, are probably busier than you've ever been.
I asked the question because all of us on the IT side can probably tell you a story where they designed, usually it's an IDF, but they put it right next to the restroom. And inevitably water winds up where you don't want it. And so everybody who's been around for a while has a story like that. It's always something you have to address. And so I thought I'd throw that out there as a.
Yeah, you're right. When we get to the third round of an RFP and we're sitting down and we've passed the procurement guys, now we're with the engineering staff, it is almost always a question. And we need to be able to talk through why we've got mitigation strategy.
Yeah, those are all great answers to that question.
Yeah.
Yeah, and on the two-phase side, that's actually one of the reasons for the robotic system. So we have water that's coming into our tank, obviously, and basically the only failure point, there's no open seam or anything in our condensers, and the only failure point would actually be puncturing that condenser. That's actually one of the reasons for the robotics on top of just general use, is to make sure that there's nothing inside of that tank that could possibly be punctured and cause a water leak. Any water leak that was outside of our tank's sealed. So it's gonna end up on the ground, and our tank is on top of a skid. So we have leak detection and things like that will give our customers plenty of time before there even is a problem. But again, the tank is sealed, and there's no way of water getting in. So that's
how do you keep those humans away, Taylor?
Yeah, exactly. I mean, I'm pretty blunt about that, right? I think computers should work for us, and we shouldn't be working on computers. We should give ourselves every ability to have the computers repair themselves and keep functioning in a way that doesn't, need humans. I think we can all agree from, all of our operators, myself included, I've plugged in a wrong network cable or unplugged the wrong hard drive when doing maintenance or whatnot, right? And if we can eliminate those unreported and unneeded errors, I think it's in benefit for all of us, right? So.
I think it's ironic how much hard work you do, Taylor, and some others to ultimately be lazy so you can get the machine to do your work for you.
No comment there. I'm a big proponent of robotics, and we at TMG Core didn't really have time to talk about it in the slides, but we are going to take the robotics, even farther than inside the auto units themselves. And we have some ideas for in the future when you need different hardware, how the autos can appropriately place hardware and things like that to give your customers, the maximum efficiency of their compute. So yeah, we're a big driver of that. We put a lot of work into taking ourselves out of a job, I guess.
Well, the good news, Taylor, is mankind is being digitized, and we are the people building and running the factories of this new revolution. So it's pretty cool.
Yeah, no, I'm super excited and super blessed to be in this industry at this time. I mean, it's amazing to see the change, and it's awesome to, see the market start pulling on that change and people being interested in, the things that we're building.
Yeah, what are the questions? Anybody who's attending, you got a great group of experts here that you won't see assembled very often. Anything else you'd like to pick their brains about? You got several hundred years of experience here.
Al, you and I used to use stone tablets to take our notes.
I have a question for Chad. What goes into your site selection for your barges? Is there like a certain area that you guys try to avoid, like too close to a coastline? Do you prefer to be like upriver, or what goes into that?
Yeah, so basically, good question. Basically, we're just like any other data center. First of all, we're not going to go place ourselves in some middle, horrible location that has, massive disasters every year. However, but with the barge solution, it's very attractive in certain locations. So first of all, in other countries, right, typically ports are the most secure. They have the most secure infrastructure as well, because that is so important for like places like Africa, even like South America, India, right? And so some of the discussions that we're having, it's an attractive solution for them because they can actually pull in to maybe places where there might be political hostility or taxation issues, right? And now they have a mobile asset. They can also use the barge solution as a temporary data center as they spend the next 18 to 20 months building a data center on land. And then once that data center on land is built, they can actually disconnect that barge and move it to another location. There's also ways to use our discharge water as well for other places. So one place on the East Coast that we're pretty far down the path on, they actually have greenhouses and salmon farms, and they're hoping to use our discharge water during the winter times for those greenhouses and salmon farms. Things like desalination as well, because again, we don't care how our discharge is used. We're not treating the water in any fashion. We're just taking it in for about 8 to 10 seconds and discharging it with a delta T of 4 degrees or lower Fahrenheit. And so the barge also, it's pretty attractive in locations that are very packed already and there's no room. So we are being able to pull into a barge in other locations like France, for instance, allows us to have some other locations. We're not as scared of industrial sectors, right? Coal-fired power plants are like a dream for us. Hydro facility plants, dream for us. Any industrial plant that already has intake and discharge is perfect for us, right? We'll just cap it with cement and use the intake and discharge, so.
Okay, thank you.
Hey, Chad, how do you handle, I mean, when you're going over salt water, it's so corrosive. Are you're able to shield the data center assets from that corrosion?
Yeah, and if anybody's interested in learning more about this, we can have a deeper discussion another time. But yes, to answer your point, we use materials, for instance, high density polyethylene, which is what the national labs use, the Navy uses, right? It's an inert piping. We use stainless steel as well. And then we also do, again, what our water treatment facilities use with UVs. We also enable a couple other things that we can chat about another time after an NDA is executed.
Oh, okay, thank you. Yes, Tony. Part of what I'm getting out of this is, and it sounds like we're drawn to it toward a close, is that it is here today, but it's interesting. I mean, it's kind of a bifurcated market, and you got colos that, as Travis is pointing out, aren't seeing much of it yet. But then we're familiar with some things that are somewhat under NDA with some of these guys that we know they're ramping up, their sales are growing, adoption is growing, and then I see the efficiency on it. My goodness, that you got wonderful efficiency numbers on these. When I first looked at liquid, I thought, oh, it's going to cost you an arm and a leg. There's no way you can afford it. But then when you look at how it actually plays out, it's more efficient than just moving the air. And that's part of what I wanted to get this out here. I think a lot of people have a lot of misconceptions. And so I thank everyone for tuning in, you guys for bringing the information. I thank our sponsor, United Private Networks, for putting up some funds to help this happen. And I hope you'll talk to these. This information will be out on our website shortly. I'm being vague there on purpose. It should be up this week, hopefully over the next few days. And you'll talk to these guys, have those more in-depth discussions if there's anything that may be of use to you, because these are some of the best of the best in terms of understanding what's going on, and it's not all intuitive. So anything else, or from our board or any of the other boards, and thank you other Texas boards for coming together. We hope this will be a model for more cooperation and broader, get more mileage out of whatever we've got to help grow AFCOM and help give back to the community. So thank you so much for giving us your time.
Thank you, Al.
Thanks, Al.
Yeah,
Thanks,
thank
Al.
you everybody for
You can
listening.
go to bed, Nigel, and the guys across the pond.
Yeah, no kidding.
Yeah, that's right. Thanks, Greg.
Yeah, good to see you, Greg.
Bye, guys.
Evening,
Bye-bye, thank you.
Bye.
night, whatever it is.
Thanks, Al.
Thank you.
Bye, guys.
Bye.
Rocking every